Okay, so we're going to continue on and finish up this module by talking about regular expressions. If we technically this goes into the next section where we talk about regular languages in more depth. But the notation is really useful, and if you look at the examples that I provided, the example problems and the practice problems, then everything is defined in terms of regular expression. So it's obviously critical that you understand them before we move on. If we look at the Chomsky hierarchy, the 4 different types of languages, the type 3 languages are the regular languages. These are the ones that have the most constraints on them. The way you build strings, there's more rules that you have to follow in order to build strings. Left-hand side contains exactly 1 non-terminal. Number of terminals on the right-hand side cannot decrease. And you have to find at least 1 grammar, at least 1 where the strings are derived from left to right, or at least 1 grammar from left to right. You could find other grammars where you're growing strings in the middle and things like that, but if you can find only 1 grammar where you're going from right to left or left to right, that's going to distinguish the regular from the context-free languages. Those of you that took CS332 hopefully will be familiar with this. We talked about regular expressions in there when we did finite state machines, and that's how we'll approach it in the next module. Okay, so we have some example languages that I've presented so far, but their definitions have been informal, like expressing it in the natural language form, all strings that end with 2 B's, or all strings that begin and end with A, or something like that. Formal systems don't allow that. Formal systems require a formal definition for everything and notation. So we're going to use regular expressions here. And then we'll borrow similar notation to talk about context-free languages. Once we get into the context-sensitive and unrestrictive, then we really can't use this model anymore. Trivia for you, all languages that are finite in size, meaning you have remember, a language is just a set of strings, and if it's a finite set of strings, all languages are of finite size or regular. And the reason is you can always just brute force, well, I say a finite state machine here, but you can always brute force a grammar where you just have a rule for every string in the language. Okay, so let's define regular expressions. This is going to be the informal format. We're going to do a recursive set definition in a minute. Notice how sets pop up again. Sets are the foundation for everything. So lambda, the empty set, is a regular expression. Any single symbol in the alphabet is a regular expression. We can concatenate 2 regular expressions together. If u and v are regular expressions, then the concatenation of uv is also regular. Notice I'm using u and v. Remember, we use u, v, and w for strings typically. Repetition. If u is in regular expression, then 0 or more copies of u is also regular expression. Now, concatenation is basically taking 2 elements, u and v, and smashing them together. What if I took u and a copy of u and smashed them together? That would be concatenation, right? Well, if we can do that, why can't we concatenate again, and again, and again, and again? That's repetition. So that's written as u star. That's this thing here. I think this thing will highlight. So we get u star. The star is known as the clean star. And so if you need 0 or more copies of some pattern, you put that star next to it. A similar version of that doesn't really have a name is this plus operator, the superscripted plus operator. This is 1 or more copies. And then the last operator we need is the OR operator. Unfortunately, the plus symbol is used both for the OR operator and for repetition. If it's superscripted, it's repetition. If it's inline, it's OR. So we can say, hey, if u and v are regular expressions, then choosing between u and v, or u or v, I guess I should more properly say, is a regular expression. And this is an exclusive OR. If you're confronted with u or v, you can't pick both. You can pick one or the other. We can formalize that a little bit, I think. Let's see. So lambda is a regular expression. Any single symbol in the alphabet is a regular expression. So if the alphabet is A is a regular expression, so is B. Concatenation. If U and V are regular expressions, then the concatenation UV is regular expression. So if I have ABBA and BBAB, then I can concatenate them and get ABBA, BBAB. This really follows, I mean, from just saying that A and B are regular expression, then obviously I could concatenate A and B to get AB, then I can concatenate ABB to get ABB, and I can concatenate ABBA to get ABBA. Similarly, I would make the BBAB side, and then I could smash those together in concatenation. Once we can do concatenation once, we can do it as much as we want, so we have the two forms of repetition. The clean star tells us that we get 0 or more copies, and the superscripted plus sign says we get 1 or more copies. So if it's like this, A star, it just means A, right? As many A's as you want. If you want to get a larger pattern together, you put a parentheses around it. So if I need ABB as my pattern that I'm interested in, and I want to make 0 or more copies of those, then I would put the parentheses around that, and I would get ABB, ABB, ABBB, I got too many B's, ABB, 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 and so on. 0 or more copies. And then similarly, for the superscripted plus sign, 1 or more copies. Okay, the OR operator, if U and V are both regular expressions, then the choice of U or V is in the regular expression. And as I said, it is unfortunate that we use the plus operator for both. A or B means you get to choose A or B. A or B star means you get multiple choices, as many as you want. And every time you choose, you can pick an A or a B. So basically, this is shorthand for any string that's composed of A's and B's. We'll have a slightly shorter version of that in a second. So any string you want that's composed of A's and B's looks like that. The correct formal definition, there we are in set notation. I'm going to say this is the set of regular expressions, and it's recursively defined. Our base case, remember recursive definitions always need a base case, and then you need to have recursive rules that make new elements in the set based on old elements in the set. So here's our base case, lambda, and our remaining base case is every symbol that's in the alphabet is a regular expression also. And then we can express concatenation recursively. U and V are in the set for all U and V that are already in the set. So right, UV is a new element, and we're composing it based on the old elements. U star, 0 or more copies, and we're basing that on the old elements. As long as you have a U that is you already know it's a regular expression, then U star is also a regular expression. Same with U plus, but instead of 0 or more copies, it's 1 or more copies, and the same with the OR operator. U or V is in the regular expression, the set of regular expressions, as long as both U and V are in the set of regular expressions. So some examples, let's assume that the alphabet is A and B. The set of all possible strings, that's that sigma star that I didn't explain earlier. Sigma star is all possible strings made from the alphabet. It's a boring language, by the way. Anytime you have nothing or everything, it's boring. You want to have some kind of discrimination. Language 1, all strings having 1 or more A. So let's see, how would that string look? Let's see, a string of just A, right, start with the shortest string. A string of just A, if you look at that regular expression, it's 0 or more B's, followed by at least 1 A, and then once we get that first A, we don't care what comes after it. So we can say, oh, okay, there's our expression for any combination of A's and B's. There's our combination for anything. So the string has to have 1 or more A. That doesn't mean it starts with an A. Well, if it doesn't start with an A, it must start with a B. And it could start with any number of B's. So there's B star. 0 or more B's. Then I get my 1A. Once I get my 1A, I don't care what happens. So I say, okay, make as many A's and B's as you like and put them in any order you like. String 2, all strings, language 2, all strings that start with two A's. There they are. I just start the string off with two A's. And once I get my two A's, I don't care what happens, so it's any sequence of A's and B's. Language 3, strings that have an even number of B's, including lambda. Now, since we included lambda in there, it means we have to have sigma, the clean star on everything so that we don't, so that we can choose to get 0 of them. But the trick is, once I get my B's, once I start getting B's, I have to make them show up in pairs. So what do? Inside this expression, notice I must get a B and I must get a B. So there's my two B's. Those two B's could be preceded or separated by any number of A's. So that's why the clean star is on the A's. And then that whole pattern can be repeated as many times as I want, 0 or more times, so that's that clean star. And once I'm done making B's, then I can just keep making A's for as long as I want, so that's that A star on the end. All strings, language 4, all strings where no two A's are adjacent, including lambda. Now, since it's including lambda, we're going to have clean stars all over the place. No two A's are adjacent. Okay, so let's take care of that criteria first. If no two A's are adjacent, that must mean that if I have my first A, I have to have at least one B before I get my second A. So instead of using the clean star, I use the plus operator. And then once I get my second A, if I'm not careful, I'm going to accidentally put an A in front of it, so I have to have at least one B following that A. So that's that expression there. Every time I get an A, I get two of them, and I can make as many copies of that as I want, and those A's are definitely separated by at least one B. I see a slight flaw in that language, and if anyone wants to point that out, please do. Now, we may not start out with we may not see any A's for a long time, so let's take care of that up front. We can make as many B's as we want. And once we're done making A's, we can keep making as many B's as we want. So technically, this could be a string that contains only B's. Have you found the flaw yet? Okay, all strings with at least 3 B's. Well, let's see. Just like before with the strings that started with 2 A's, well, there they are. I just dumped them right in the front. Once I get my 2 A's, I don't care what happens. This is a little bit less restrictive because I'm not saying it starts with 3 B's. I'm saying that it has to have 3 B's somewhere in there. So it's a little more complicated to make that happen. What I'm doing is enforcing that when I make this string, it has 3 B's in it. But because there's no restrictions on the A's, then I have to put, okay, I might start a string with a whole bunch of A's, so I better put that in there. Then I get a B, then I could potentially have a whole bunch more A's. Then I get a B, potentially a whole bunch more A's, then a B. Now that I've got my 3 B's, I don't care what happens, so there's my standard notation for any combination of A's and B's. Notice there's no clean star here. I don't need to do any repetition. If I put a clean star here, by the way, I could choose to make that pattern appear 0 times, and now I would have a string that does not have 3 B's in it, which violates the rule. I could put a plus in there and keep doing that pattern over and over again, but then what I'm doing is I'm creating B's in groups of 3, and that's not the rule either. It's just at least 3 B's. Okay, so we'll do that once, and then once we do that one time to get the 3 B's in there, we don't care what happens. Okay, so there's some introduction to regular expressions, and we'll spend a fair amount of time just doing lots of examples. The way to get good at this is to do lots of examples so you don't make a mistake like I made here. Have you found it yet? Look on the PDF notes. There are example problems and there are also practice problems. So the example problems, I'm working them out for you. The practice problems, I'm just giving you a bunch of problems to look at for you to think about how you might create these languages. Okay, I will see you soon.